All right, welcome back. This is now part three of the series for thermodynamic cycles. Last time we talked about power cycles and we cited an example, which was the Rankine cycle. So now we will flip things around and we will talk about reversed cycles. And you might think about it, reversed what? So, I mean, basically, it's a reversed power cycle. And it's reversed not in the way that you would think of normally, right? There's a lot of things that can be reversed in a reversed cycle, right? More specifically, what the signs of maybe the heat in the work, what it does, and basically a reversed cycle, for the lack of a better term, is a cycle where you do work on the system or you do work on the cycle. And what that means is basically in this case, whenever you have an open system, you give it electricity, right? You provide it with electricity, and that is the work input. And because of that, right, now that we mentioned a work input, that means that you're going to have to give work to the system. That means that your work net is going to be negative, which by the first law for cycles, that means that also your heat net is going to be negative. Now, if you think about it, what does this mean? Your heat net is negative. What does that mean, right? In this case, that means that you give work to the system. You do work on the system. You consume electricity for the system so that you can achieve a reversed flow of heat. What do you mean reversed flow of heat? That is the definition why the reversed cycle is called the way that it is, right? We know that heat flows from hot to cold, right? That is something that we've been saying since what? Like since we were elementary school students, maybe high school students, something like that. With a little external work, or basically with the presence of any external work, we can flip that. We can now say that heat can flow from cold to hot so long as we provide the system, or we provide a device with work, right? It's very interesting. It's a very interesting premise, and well, that is the reason why right now I have my air conditioner on. Right, it's now making my room just a little bit colder. Right now it is 29 degrees Celsius. When I stop talking for this section, maybe I'll give you guys a little update as to what the temperature is now. Right, and so in this case, we have these two people to thank. Maybe I suppose for our next example, right? We have here Oliver Evans. He's a very prolific inventor, so much so that he was called the Watt of America, right? Watt as in James Watt, right? The I forgot what he was. He's not British. He's Scottish, I think. I don't know, right? But the thing is, Oliver Evans was the one who first thought of what we call the vapor compression system. What you mean the vapor compression system? Well, the vapor compression system is the air conditioning system. It's the refrigeration system, right? And if Evans was the one to first think about it, Jacob Perkins was the first one to actually do it. Both of them American, very interesting. He built the first working closed cycle vapor compression system using what he called volatile fluids. Now we have a standardized name for that, and that is what we call refrigerants. The things that are coursing through our refrigerators, the thing that is coursing through my refrigerator and my air conditioner right now, because both of those things are on, right? That is what enables basically comfort, cooling, and refrigeration for everything all around the world, right? Almost everything, right? And so now our example will be the reversed cycle, the vapor compression cycle, right? I won't go into much detail in here, and I will trust me guys, you will not be solving for anything involving a vapor compression cycle, right? But I just want to show you how this can be done and how this is usually done in the real world. This is a reversed cycle using the vaporization properties of refrigerants, or what Perkins has called volatile fluids, to manipulate heat flow via work. Basically, the thing about refrigerants is that they can vaporize. Okay, wow, very special thing. Even water can vaporize. What is so special about refrigerants? The thing that is so special about refrigerants is the fact that they can vaporize at room temperature, right? Most refrigerants have boiling points just about, right, below room temperature, and sometimes even in the negative degrees Celsius, right? So that is really low, and that means that they can vaporize very quickly. Why does that matter? It's because right? If you remember, when you vaporize something, when you turn a liquid into a vapor, you're going to need a lot of energy. Where are they going to get that energy? We'll find about it later, right? But in this case, the code of a vapor compression cycle is going to be SPHP, right? As you can see here, isentropic, that means an S, an isobaric, which means a P, an isenthalpic, which means an H, very interesting, then an isobaric, which is a P, right? And so let's see how this is going to happen. This is another open system cycle, right? Or basically, you're going to have to analyze the cycle using steady flow devices, as you can see in here, right? As you can see in here, right? There are 4 steady flow devices there. And so we begin with the heat source again, but now it's at the bottom. This is what we call the evaporator. And for the lack of a better term, the evaporator is what we see when we have an air conditioner on, right? An evaporator is basically in a window type air conditioner. This is the thing facing us, right? This is the thing with the panel, the one with the vent blowing hot air. Blowing cold air out, right? And then you might say to yourself, okay, it's blowing cold air out. Who cares, right? The thing about the evaporator is that it does not only do that. What it does actually is that it's trying to absorb heat from us, which is the cold space, which now you might say, oh, okay, this is where the reversed heat flow comes from. Notably, what you're supposed to do normally is that you're supposed to get a heat source, or rather your heat is supposed to be obtained from a hot source. You're not supposed to get it from a cold source. The thing is, this is now made possible because of the fact that it is connected to a compressor, right? State 1 in here, based on the name evaporator, just like in a condenser, state 1 in here, the output of an evaporator is going to be a saturated vapor. Most of the time, this thing is going to be a superheated vapor, but let's just assume that this is going to be a saturated vapor for now. Either way works, right? But what happens here is that, why did it evaporate? It's because it got a lot of energy from us. What happens is that not only does it blow hot air, it actually absorbs the heat, right? The heat from us in the room, right? Whoever is that is emitting heat, maybe me, maybe my pets, maybe this computer, which of course is going to consume electricity, is going to be a little bit hot, right? That is what it is absorbing. That energy is enough for the refrigerant to vaporize, and then that vapor is what will be compressed by the compressor. You might say to yourself, okay, you're giving work to this compressor. Why? Right? Well, now the goal is, okay, congratulations, you have now absorbed energy from the cold space. What are you going to do? Are you just going to hold on to that energy? Of course not. You need to find a way to throw it out. But the thing is, you're supposed to throw it out normally in the cold space because, well, you reject heat like that. How are you now going to throw it out? You're now going to throw it out to the reverse, to the hot place, to the ambient air outside. How are you going to do that? Well, you're going to compress it, not only so that it will become a higher pressure, but also so that it becomes just a little bit hotter, right? When you compress a fluid, when you compress an ideal gas, right? If you just want to think about it in a more pure sense, right? If you compress an ideal gas, what will happen most likely, because this is a, what do you call this? This is an isentropic process, as we'll see later. What will happen is that it'll get a little bit hotter, right? Just a little bit hotter, so that at state 2, it is still a superheated vapor. It will now enter the condenser. Okay, what then, right? If it's a little bit hotter, then if it's a little bit hotter than the ambient air, it can now exchange heat with the environment. More specifically, it can now throw away heat to the ambient air. That is what you need to do. That is how we can take heat from a cold space and throw it out to a hot space. We need to be able to provide this system with some work. That is the essence of a reversed cycle. Right now, right, we will route it back to our evaporator. And how do we do that? Well, we can now condense this. We can now reject, right, the heat in the vapor. And so what will come out of state 3 is going to be a saturated liquid. Right? It's going to be saturated liquid right here in state 3, but this is of a high pressure. This is of a high pressure because this condenser is an isobaric process, and this compressor, what it did was that it increased the pressure. So now in this case for state 3, what will happen is it will go through and flow through the expansion valve. The expansion valve is basically a valve, right? It's just a thing, right? Such that you maintain a pressure difference from the high side, from the condenser side, and the evaporator side. Without this expansion valve, this system, this cycle will not have an appreciable pressure difference, and well, the system, or rather the cycle, will not work. Now notice the expansion valve does not have a heat or a work that is coming into or out of the device. Why is that? That is because your expansion valve is an isenthalpic process. No energy is lost or is gained between pressure states 3 or 4. That is how a vapor compression system works. And in this case, a reverse cycle can actually be operated two different ways. Right? Here we have. Oh, sorry. Before we do that, right? Let's add a little bit more detail in here. Right? A compressor in this case is going to be an isentropic process. Right? And you're taking in here a low pressure vapor, right? A low pressure vapor that you just evaporated from the evaporator earlier, so that you're going to increase its pressure, right? Not only are you going to increase its pressure, you will also increase its temperature. And more likely than not, your state 2 will be hotter than the ambient air, and you can now successfully reject it isobarically in the condenser. Right? What will happen now is that at state 3, right, you will see that the pressures at state 2 and state 3 are the same. You can regard them as the high side pressure. And in state 3, what you will have is the output of condenser that is going to be a saturated liquid, right? And from state 3 to state 4, you will notice that you are now entering an isenthalpic process. And that means that no energy will go into or out of the system. What will just happen is that the enthalpy will remain the same, but your pressure will decrease. Your pressure at state 3 will now become a lower pressure at state 4. That is the only thing that will happen. And now, right, your state 4, because you decrease the pressure, we can look at the diagram later, it will become a two-phase mixture. And now we perpetuate, right? We perpetuate the cycle by using an isobaric process, an evaporator, so that you gain heat from the environment, and there's the cycle. Right? You will have pressures 4 and pressures 1 being identical, that you will regard as the low side pressure. So just like before, it seems like this is kind of the same, or this is similar to the Rankine cycle, in which you have two different pressures that you are operating on. And I suppose that is the only kind of similarity that I can really see, right? Well, you have 3 out of 4 processes that are similar, right? You have 2 isobaric process, you have 1 isentropic process. Perhaps the main difference right here is the appearance of the expansion valve. Okay? And now, this is what I meant to say earlier when I said that there were 2 ways to operate a reversed cycle, right? Of course, this is the more popular way of operating it. If you want to be cold in a hot place, what you will do is you will stand in front of the evaporator so that you will be cooled, I suppose, right? This is what we normally do, especially in tropical countries with high temperatures, when we just want some comfort via cold, right? You stand in front of the evaporator, that evaporator will cool the space that it is in. Conversely, if you are in a very cold environment, well, you can just stand in front of the condenser, because the condenser rejects heat to the environment. It rejects heat to you. And so if you want to be heated, you can also use a reversed cycle to generate this heat. But at this point, like, just, set fire to a bunch of sticks, then you will be hot as well. So maybe this is a non-dangerous way of thinking about it, maybe. But anyway, right? You can operate a reversed cycle like this, and this is what we call a heat pump, right? Heat pump, because literally you are pumping heat from a source so that you will be given heat, right? That is what we're doing in here. Okay, and so we continue, and now we will talk about a diagram. And in this case, the diagram is it's not a PV diagram, it's a pH diagram. So in this case, a pH diagram is a diagram that it may be, right, that is specifically made so that we can analyze reversed systems just a little bit, or reversed cycles just a little bit better. Okay, and now you might notice, okay, is there some interesting thing about the pH diagram? Maybe is the area something very different? No, there's nothing special about the area, right? If you're going to multiply P and H, right, which signifies the area of this graph, you will not get anything important. In this case, your pressure is in kPa, maybe. Your H is in kilojoules per kilogram. And in this case, what you can do with the kPa is you can kilonewton per meter squared it. Right? For the kilojoule, you can turn it into kilonewton per meter. And then you can retain the kilogram in here. And well, you're not going to see anything important crop up. Maybe you can cancel this. I don't know. Right? But in this case, you now have 2 copies of kilonewton on top. It's not going to be anything very important, right? What's important rather is the fact that for a lot of refrigerants, for many refrigerants out there, you can already see, right, an existing pH diagram wherein you can draw on the diagram, right? So right? Say for example, we have here an app called the Cool Selector 2 that is by Danfoss, right? This is a company using, or rather tackling, the imaging, maybe, or what do you call this? The HVAC industry in general, right? We have here R22. This is the pH diagram for R22, and what we notice is that, well, with a lot of these diagrams, and basically for all of these, oh my goodness, for a lot of these diagrams, you will see that as opposed to a saturation region that is, straight up, it's a little bit erect, right? What is happening with a pH diagram is that it's leaning to the right, right? So if ever you're going to draw a pH diagram in the future, know that it is leaning just a little bit to the right. So here we have propane. Here we have R134A. Here we have R22. Here we have 717, that is ammonia. Here we have water, right? You can have water in as well. And basically, yeah, a lot of things in here. Okay, this is isobutane. This is oh my goodness. This is the current refrigerant that I have for my refrigerator. So that's always very interesting to look at. I think R23 is the refrigerant that is coursing through my air conditioner, right? But I'm gonna have to check on that. Either it's R23 or R32. But anyway, right? We go back here. The thing with the pH diagram is that you guys have seen it, right? The saturation curve is going to be a little bit wonky, right? It's going to be a little bit leaning to the right, but nevertheless, right? We have seen that pressures 2 and 3 are the same. They are the high side pressure, and pressures 4 and 1 are going to be the low side pressure. We will start our analysis with state 1, which is now going to be here. We know that state 1 is going to be either a saturated vapor or a superheated vapor at the low side pressure. So I've just kept it to be here. And actually, it would be very inconvenient that we have exited the cool selector, because, right, I want to show you guys as well what the different processes look like here. Say for example, we have R134A. As you can notice, there are lots of different colors in here, right? The color black represents either the saturation line. So on the left side, you would have your saturated liquid side. On the right side, you would have your saturated vapor. And then these thin black lines correspond to different kinds of quality. So 10, 20, 30, right? 50, 60, 70, 80, 90%. dryness, right? The blue lines mean uh, entropy lines, right? They are constant entropy lines. So you can see here S equals 1.75, 1.8, so on and so forth. And what you will notice now is that they are basically like lines that are very steep going up. There's going to be a little bit of curvature, especially if you're going to look at this left-hand side of the pH diagram. But for now, let's just draw it like this, right? That's what I'm going to draw an isentrope to be, right? That is a line of constant entropy. And now wherever that meets with the high side pressure, we will stop and we will call that your state 2. Okay, that is now at the high side pressure, and notice that this is now going to be very hot. Speaking of hotness, the red lines correspond to temperature. Right, so notice that the temperature in here will of course stay the same because of saturation, but in this case, right, your 30 dips really far down very quickly. So that is how you're going to read your temperature. And finally, the green lines in here, the ones that are sweeping to the right, those are going to be specific volume lines. Okay. All right. So that's going to be how we read these pH diagrams. And I will return to my slides here. And now this is the condenser, right? The output of a condenser is always going to be a saturated liquid, right? And then on process 3 to 4, note that in this case, this is an isenthalpic process. This is an isenthalpic process, which means, right, your H coordinate or your X coordinate will remain the same. This is why this is just a straight line downward. This is now from this is now from state 3 to state 4. And then finally, from 4 to 1, this is going to be another isobaric process. So you just connect the two lines and you will have this, right? Now, the thing about this is that, why did we look at this manifestation of the cycle, right? Why not just the PV diagram? Why not just the TS diagram? Well, the thing about the pH diagram is that it declares, or rather it shows you very quickly, right, the change of the energy of the system. What do you mean? Right? I will invoke the first law for open systems because we are looking at this in an open systems perspective. And we know that your KE and PE are going to be negligible, so we can just cancel those out. Note that what happens now is that Q minus W is equal to delta H. The change, right, in enthalpy of any process dictates the amount of energy that is going into or out of the system, right? In this case, either it's going to be some energy through heat or energy through work. Now, notice what happens from state 4 to state 1. That is process 4 to 1. That is going to be the heat addition, the QA. Notice that you are reading 4 to 1 from left to right. There has been an increase of energy. Note, look at this, H4, and then this is H1. Of course, H1 is going to be a higher enthalpy that is now described by this line. Note that in this case that your QA is added to the system. Therefore, it's going to be treated as a positive. Okay? Now, next we go around the cycle again. We will now see this this compression work, right? Work of compression. Now you notice from H1 to H2 that there's again going to be an increase in enthalpy. This much, right? Now notice that your WC in here is going to be negative, right? It's going to be negative because you're putting work into the system. But in this case, we are not caring about the sign. More specifically, we're just looking at how much energy is currently in the fluid as it is flowing through this system, right? So long as you are pouring energy into the fluid, that's going to be an addition, right? Speaking of addition, what will now happen in here for state 2 to state 3 is going to be a pure subtraction. You are going to let heat out because you are condensing the fluid at state 2. What will happen now is that from state 2 to 3, you are now reading it from right to left. There's going to be a marked decrease in the energy or in the enthalpy of your fluid, and that is described by this length. Now notice, why did I highlight those three lengths right here? It's because if you look at these guys, right, and if you look at them in tandem with one another, you will see that you add, right, you add QA, right, the energy will increase like this. You add WC, the energy will increase like this. And then you throw all of that energy out, and then the process repeats itself again and again. This is just going to be the first law for cycles, right? Notice that net, the heat net, in this case, this is going to be adding this amount of heat, and then this is going to be subtracting this amount of heat. So basically, these two will cancel themselves out. You will leave yourself with this amount of net heat. And look at that. That net heat is going to be negative. It's going to be heat that you are going to reject from the system. Why is that? It's because your net work was also negative. Negative in the sense that, well, you are putting energy in the system. So that validates our definition for the reversed cycle, right? The reversed cycle, which says that, well, net heat is equal to net work. If you're going to put work in the system, expect that some heat will be rejected from the system as well. That is going to be translating as a reversed flow of heat. Okay? And so we proceed, right? Because now what we want to find out is a measured performance for a reversed cycle. And so again, the concept of efficiency is output over input. Let us remind ourselves what the input and the output is for a reversed cycle. A reversed cycle is basically where you do a cycle where you do work on the system or on the cycle, right? And so that means you do work, meaning your input is actually going to be your net work, right? You're going to work on the cycle, and basically you can choose between any of the two outputs, either your QA or your QR. If you want to be cooled, your output is QA, and it just so happens that QR is a byproduct. Conversely, if you want to be heated up, your QR is your output, and your QA is just a byproduct. Okay, that is your reversed cycle. And so now we can hone our definition of efficiency. We can actually define two different ways, right? And two different measures of performance depending on what it is that you want to do. The more famous one is the coefficient of performance, or the COP. The coefficient of performance is basically a measured performance of a reversed cycle by dividing its heat absorbed, so this is for refrigeration or air conditioning cycles, over the input work. Your COP basically tells you how well you can absorb heat based on the amount of work that you're going to do on the system, based on the amount of electricity that you are going to supply. And conversely, the performance factor is now for heating systems. The measured performance of a reversed cycle by dividing its heat rejected over the input work. Basically, performance factor tells you how much heat you can receive, how much heat can be rejected to you based on the amount of electricity that you're going to give the system. Right? So we are going to focus here, of course, because well, it's going to be very rare for us to try and understand or try and use PF, especially for a tropical country like the Philippines, right? But yeah, we can now say that our input is your work of compression right here, this length right here. And you have two possible outputs. One is the heat that you have absorbed for refrigeration systems, and QR, right? The heat that you have rejected for heating systems. And so now, if you're thinking ahead, wait a second, the COP is going to be QA over work net. That's going to be this over this. And for PF, right, your performance factor is going to be QR over work net. It's going to be this length over this. The thing about this is that my drawing is not that out of scale, right? It's a little bit out of scale, and I just wanted to actually bump up the length of the work of compression, because otherwise it would be too small to write down the words the letters WC. But the thing about this is that for both of these factors, for both of these coefficients, your numerator is going to be bigger than your denominator. Yes, right? What we want is as much bang for our buck. If you think about it, a COP of 1 is going to say, or rather, what it says basically is that if you give out 100 kilowatts of power, you're only going to absorb 100 kilowatts of heating, of cooling, pala rather, right? The air conditioner is only going to provide you with 100 kilowatts of of cooling. The thing about this is that COP normally goes above, right, 1. Okay? And so that doesn't mean that a lower COP is bad. At the very least, it provides some cooling, right? But in this case, right, COPs for domestic refrigerators or domestic air conditioners are at about 2, 3, or 4, right? Sometimes 5 is a little bit too high. It's a little bit suspiciously high, but we can take that, right? And PF is also around the same value, okay? It's a little bit higher, of course, right? And we'll discover why that is later. But yeah, you want your COP to be high. You want it to be as high as you can. And perhaps we are a little bit confused here, or rather, your first reaction might be a little bit of confusion because the version of this for power cycles is always going to be less than or equal to 100%. But now you've been told in here that, well, it can go up, what, 2.5, 3, 3.5. That's a little bit interesting at the very least to say, right? So that is the difference, the main difference between thermal efficiency and COP and PF. Okay, and just like before, right, in this case, a vapor compression cycle, just like any reversed cycle, is usually drawn, right, using the steady flow device itself. However, again, you are the one to pick what you want to study. So if you want to study the whole cycle, then draw a system boundary over the whole cycle. What will then happen is that you can now reduce, or rather simplify, your vapor compression cycle, and you don't even need to know what is inside of it. You just know that you are going to have to supply it with some compressor work, and what will happen is that you will absorb some heat from a cold place and reject that heat to a hot place. And so, furthermore, right, the simplification for any reversed cycle, not just a vapor compression cycle, will be you give it work and you will be able to access cooling, either cooling or, in this case, heating. Okay? And so now we will go on into the second law. Right? This is the end of this section, and next section we will tackle the second law, and we will tackle one of its restatements, which is the Kelvin-Planck statement. And of course, we will now also tackle the perfect cycle, the Carnot cycles. Okay? I will see you then. Thank you very much.